Okay, thank you very much for having me here today. And yes, so I will start, actually, I will start first with a question and then we can get more into the details. And you should see like the full screen is it's a blank slide at the moment. Is that correct? Can you see it? Okay, perfect. So yeah, so I would like to start with a very simple and almost trivial question, which unfortunately we cannot really address because we are via Zoom. But many times when I start with this type of presentation, I like to ask people like, how tall am I? And of course, we are via Zoom, so you cannot even see it. But I think you can already see that there is a pretty big problem here, and is that the three possible answers are actually without any unit of measurement. So I just like 180, 5'9", and the common question that everyone would ask is like, yes, you say like 180, but 180 of what? I think like we learned all this in high school. Like also my teacher used to be very heavy on this. Like you cannot just report numbers. Okay, so this is very trivial. And also it's trivial, the fact that the same object, in this case me, can produce like different numbers, even if we're measuring exactly the same thing. So we're measuring height, and this is like my height in meters, this is in feet, this is in parsec. Of course, you will never measure a person in parsec, but eventually you can convert. Okay, so no surprises here. But here we start having actually the interesting thing, because if we look at how we make models, and especially like I work with opinion dynamics models, we have that many times we say that, for example, an agent's opinion is 0.6. But nobody here asks like, 0.6 of what? And this is an interesting point. Why do we actually are so, let's say, rigid with simple measurement like height, and then we are very flexible, some way like we do not need to report the unit of measurement for something as complex as opinions? And the simple answer is like, we don't ask this question because opinions, as many other things like happiness, stubbornness, and all the psychological variables, they have no units of measurements. But this is an important distinction. Like, it's not that they do not have units of measurements, because they are so simple that you do not even need to report a unit. But it's because actually their measurement system is so complex that we cannot even define a unit of measurement for these things. And so if you look at the history, today we will see a tiny bit of this, we actually had to come up with an entire different way of measuring these constructs, which actually cannot rely on the classical things of units of measurements. So this is going to be like crucial for today. We have some variables which have like an entire different measurement system. And so we cannot treat them as if they were simply physical measurements. And if we do this, we will see like we will have some very surprising results. So this was the introduction, just to try to get to understand like what we will talk today. And so today I will talk about ordinality, which we will see in a moment is a property of psychological measurements, and how ordinality can actually create some very big problems if we don't treat it correctly, and how we can use it actually to solve a lot of these problems once we understand actually what is happening with the data. So I think people have many different backgrounds. So maybe you're not familiar with this. This is mostly developed in psychology and in psychometrics, which is like how you measure psychological constructs. And usually they divide between 4 different types of measurements. There are like ratio, interval. These are the ones which have like standard unit of measurements, like meters, Celsius, etc. Then you have nominal, which are just categorization. So for example, if you want to categorize something, some people by gender, you will have that this is like a nominal measurement. And then we will have what we will focus on today, which is ordinal. And ordinal are a very special type of measurement because with ordinal, you can always say what is bigger, but you cannot say how big it is. Let me give you an example. Let's say I have some answers to a survey and some people are reporting their level of happiness. And some people say they're happy, some people, they say they're sad. So we can say that happy is some way like bigger than sad. And if we also put like a neutral level, we can put them in order. We can say like there is sad, neutral, and happy. The problem is we cannot say what is the gap between which one of this step. We cannot say that if you move from neutral to happy, you are 3 times or 10 times happier. We can just say that you are happier, but we cannot quantify how much happier you are. This eventually generates some problems when we notice that actually when we make models with agent-based models, we usually model pretty much all the variables as interval or ratio. So we suppose like there is like a continuous dynamics. You can have like, you can average them, you can know how much one is increasing, etc. So we treat the variables as interval and ratio, but actually the real data that, for example, quantify opinions and the real data which are used, for example, to say that opinions are getting polarized in the United States are actually ordinal data. So we might have a problem here, and we need to study what happens when we have like this, this distinction between the variables and the data. Now, a couple of things to clarify. First of all, sometimes you can have these ordinal variables and you can process them, for example, by using factor analysis or something like this. And some people think that if you process ordinal variables, they will become, for example, interval. Unfortunately, this is a misconception. If they're ordinal, like your original data are ordinal, they will stay ordinal even when you process them and you get some very fine-tuned numbers. And this is for this following reason, because actually ordinality is actually not a property of the data, but it's a relationship between the data and what you want to measure. Let me also give you an example here. So let's say you want to measure happiness, but the problem is you cannot directly measure happiness. We do not have a happiness meter that we can inject in a person and say like how happy they are. So what do we do is that instead we can measure things like smiling. And so we can say like, oh, this person today is smiling 10 times. The following day is smiling 20 times. So what we can say is that the person is happier. So what we can assume is that if smiling increases, then also happiness increases. But the problem is we cannot assume that the relationship is going to be linear, which means like if you smile twice more, you're also twice as happy. And this is pretty much ordinality. What ordinality is telling you is that there is a relationship between your data and what you want to actually measure. And the relationship might be ordinal, but you cannot say that it's going to be linear. And we can even visualize this. So for example, here in one study we made, we collected data on trust in science, and then we created 2 scales of trust in science by just changing the items, the questions that people were going to respond. And then we see like how each person scored on each one of the two scales. So you can see like people who scored 4 on the first scale also on average scored 4 on the other scale. And people who scored 6 on the average scored 6 on the other scale. And you would expect this to be linear, like people who score 10 on one scale, they should score 10 on the other scale. But actually what we can see here is that the behavior is actually non-linear. You have that at a certain point, it diverges from the straight line and it gets like this bump here. So I think like people with the background in physics should be pretty comfortable with this nonlinear transformation, but eventually, like, I don't know, again, the background of each one, but one way to visualize this is with the use of these distorted mirrors that maybe like you have seen at fairs where you stand in front of the mirror and they completely distort the proportions of your body. And what is interesting about these mirrors is that what they do is that they destroy proportions, but they preserve ordinality because your head is always going to be above your shoulders, which are going to be above your legs, for example. So what you can imagine is that when you make a measurement and you want to measure, for example, happiness or opinions, you do not get actually the right values of opinions, but you get a distorted version of this. It's almost like you are looking at them through one of these distorted mirrors. And this is important, like every person which makes a measurement of this is going to get a different distortion. So for example, if there are 3 people, unfortunately, like in this image, I should get a better image because the person is also changing their position. But if we have 3 scientists and 3 scientists measure exactly the same population and the same construct, so for example, happiness, they will end up with different distortions unless they use exactly the same measurement system. And so what we have is that from changing from one measurement system to the other, we will have to apply some of these distortions. Also, just in case, because I know some people think like, oh, then we should get like the ground truth. Even if you suppose there is a ground truth, like a real value of happiness, the problem is you cannot get it. So because we only can deal with measurements, and so measurements are distorted. And so you can never really reconstruct the real level of happiness. You can only have like this distorted version. But the good thing is that this distorted is not like they're completely random. It's just like we know that they are still in order compared to the real value, or at least they're in order compared to the other. So this means that if these are my data and I want to compare with the data of another person, I need to apply these distortions. Eventually, we can think of this as when we make a measurement, it's almost like we are casting happiness or whatever into a different space. And so every time we want to move to another measurement system, we have to go in a new space. And to move to one space to the other, we have to go through one of these transformations, which is, for example, what has been visualized here, this kind of transformations. So just like in physics, if you want to convert from meters to kilometers, you multiply. Here, you have to transform. It's more complex, but at the end is pretty much the same idea. It's just an extra level of complexity, which unfortunately is not nice, but it is what it is with this kind of measurements. Okay, so how does this impact agent-based models? Because right now I was just explaining psychometrics. So we also studied how this will impact agent-based models. And before actually showing the impact on ABMs, I want to show some very simplified environments. And so here I'm just simulating a point, or a ball if you want, swiping up and down. I can show the video. I don't know if it's lagging or not, but the point is just moving up and down. And here you can see like its dynamics in time. On the x-axis, you have time. On the y-axis, you have like the value, the position of the ball. And you see you have a nice sinusoidal pattern. The question now is like how this pattern would look like if we look at the same phenomenon, so the point just swiping up and down, through a distorted mirror. And I'm applying this transformation, which is x to the fourth power. You can apply whatever you want. But in this case, what we have is that the dynamics looks very different, because what is happening is like everything is being squeezed close to zero. And by the way, the extremes are still the same. It's still between 0 and 1. But what happens is that now it looks like the ball, I can play it again, the ball is staying on the ground and then is jumping very quickly up and coming back down. So this eventually generates even a different qualitative behavior. And this is important because many times with agent-based models, we say like, oh, we can qualitatively reproduce this behavior. What we have here is that if you cast a different space, like you put your model, your phenomenon in a different space, you will have a completely different dynamics. Notice that it's still going up and down. You do not have like that is going some other weird things, but it is qualitatively different. And we can have another transformation here. And what you have is that, for example, now the ball is stopping at the center and then going up, and then stopping at the center and then going down. Now, we can simulate something like this in agent-based models. And what I'm doing here, I'm supposing that there is like an absolute space where people follow a specific model, which in this case is the font model. And then I'm simulating how a person would measure the dynamics in another measurement system. So it would be like in another space with some distortions compared to the first space. So let's suppose people are really following the font model. How would it look like for different scientists? And here, I hope the video quality is not terrible, but what you can see is that 4 different scientists will observe 4 different behaviors. So in one case, we have that everything converges to unimodal. In this case, converges to bimodal. And then also here we have some other skewed distribution. So this is a very big impact, because what this tells you is that what can be unimodal in one measurement system, it can actually be bimodal in another measurement system, depending on how you measure things. So the impact might be very big. And so in general, if you want to think about this in a broader way, you have that even if you suppose that people are following the dynamics of your model, the problem is when you collect the data, data would be in a distorted space. And unless you are very lucky, the space in which you, some way like you made your simulation might be very different from the space in which you are measuring. And so you can get a very different dynamics. And something that might happen even is that maybe like you make a model, your model, you calibrate, you do predictions with your model on a data set, which is in a certain space, and maybe your model works very well. This might be, for example, very important for policy application. Let's say you develop your model is working amazingly, and then you apply your model to a different context or a different data set. And now your model starts behaving very poorly. Why is that? Because actually, it might be that the space of the first data set is not the same space as the second data set. And so like the dynamics now is behaving differently. So again, just to get a different perspective, what people usually think with agent-based models, especially if they want to merge them with data, is that either your model is a good description of the data or it's not. What we can see now is that actually there is an extra variable to take into account, because your model might be actually exact in a certain space, but actually it might be completely wrong in many other different spaces. And so what you measure, it might be completely different, even if technically you are right. Unfortunately, I'm not tracking time. How much time do I have left?
You have some, no, not really much.
Okay, I will conclude very quickly then. Okay, just rapidly, we also explore kind of the complementary version of this. And we said, like, what happens if we take abstract models? So before we were mostly focusing on data. What happens if we focus on the models and we add one variable which actually can transform the space? The only thing that it means is that you take your opinion space, for example, and you apply a nonlinear transformation. So what happens? Well, what we noticed was that there were these three models from Hexelman and Krause, which have been defined in this article. And in this article, actually, the authors studied these three models. But actually, these are the same model, just in three different spaces. So if you transform from one measurement space to the other, you can convert one model to the other. And we proved this mathematically with simulations, etc. Let me just tell you like how we can use this to solve the problem. So the problem we saw before was like, technically, we have a problem with the data, because even if we suppose the best scenario, in which our model really represents the dynamics of the people, we still have one extra variable, which is when we measure, we will get a random space. And this space might not coincide with the space which we model. So what can we do? We can actually add an extra variable to our model, which actually generates distortion of the space. And if we do this, we can calibrate our model to actually match the right space. This would be equivalent like when you make a mathematical model, for example, and you do not want to specify if the model is in meters, kilometers. You just put an alpha, a variable there, and you say like later we can calibrate and we can specify this variable according to the measurement system. Just in this case is a function instead of a variable. And so the take-home message for today is that sometimes people think like, oh, you should not use ordinal data for interval variables. So some people complain when we use psychological data with opinion dynamics models, for example, or agent-based models in general. Some people directly do it and they don't care. What we should actually do is that we can actually merge them, but we need to be careful of the fact that we can have nonlinear transformations. And so we can tune the space in such a way that we can match between the space of the data and the space of our models. And yes, with that, I just conclude. A lot of this is explained in this paper where we tried really to go step by step to explain like psychometrics and how this fits with opinion dynamics models. And that's it. If you have any question, please let me know.